So we now get to chapter 16, talk about the PicoBlaze assembly language development. Hopefully everybody is staying with me. Now for us, of course, we have the Tramelblaze, we have our own assemblers, so it's not going to be exactly the same. What I want to do is show you the differences to make sure that you're comfortable. Coming down, first talking about conventions, comments are the same, all of our values are default hex. And what I want to point out is that whenever you have a label for an equate or a label for a statement, please put the label in column 1. If you don't, it's not going to work. So remember, labels go in column 1. And conversely, never put an opcode in column 1. So in essence, if the assembler sees a value in column 1 that is A to Z, it will consider that to be a label. So now he's talking about some of the code. The first thing he shows is a jump. Keep in mind my instruction set's a little different. So the jump space Z becomes jump Z. References to register are not S but R. I thought that was a little more intuitive. When you have to declare constants, please use an equate. So you'd use the label, the keyword EQU, and then the value you want equated. So same thing with a name reg, use equate. Just make sure that the register that you're defining is R0 through RF. In the control, there's a variety of different structures. What he's showing basically, which I appreciate, is the high-level language type of constructs that he's then able to implement in the assembly code. Eventually he's going to call this his pseudocode. I highly recommend documenting your code before you write it in the form of pseudocode, then utilizing that pseudocode interspersed in your source code as comments to be the description of what each functional block will do. So without a doubt, we need to utilize subroutines. The PicoBlaze uses the call and return instructions to implement a subroutine, so also the Tramelblaze. The call instruction will save the current content of the program counter, which is PC+1 already, and will transfer the control to the address referenced in the call. The subroutine ends with a return, and that will then cause the flow to return to the instruction immediately after the call was executed. For our program development right now, I don't think we've dug in too deeply here, but I really think his recommendation of the program development flow is worthy of practicing. That develop the pseudocode first as a documentation of what you want to do. In the past, people use flowcharts. Flowcharts proved to be problematic with respect to maintaining the contents of the flowcharts relative to what the code eventually evolves to. Pseudocode using a text editor to be created is much easier to update. So document your code before you write it. Identify what you can break out into subroutines. For more complicated tasks, have subroutines. Determine how you want to use the registers, how you want to use the data RAM. The registers for variables, you have 16 registers available. You have 512 locations in the RAM. So if you have data storage that you need, but you've run out of room in your register file, you should use the RAM. So this is documenting how you plan it out and then how you write it. Remember, Our syntax is a little different, so here I'm just demonstrating for constant definition, use the equates. Again, I like the code. He has a nice little header portion above each code block. My preference would be the pseudocode is found here. So you get a description of what it is you're doing. You demonstrate the algorithm in the pseudocode, and then you have the code to implement it. Without a doubt, assembly code programming is tedious. Do your best to take the edge off. You can use symbolic names for the registers or for the memory locations. Just organize your approach so that you don't find yourself reusing registers unknowingly and then having the contents change unexpectedly. Have a good plan, have a good documentation. In the Verilog, I've given you guys a header that I want you to use to implement your design. Here in the assembly code, I haven't. Pong makes a recommendation of what should be contained in a program header. There should be the description of the program, what it is you're doing, what it does, any data constants that you're using, any RAM utilization within the memory, within the processor, how you're using the registers, how you're using the ports, and the calling structure and the subroutines. Have a nice header. Also, I would say you should have your edit history there, who authored the code, and as you come back to touch it, each time you should update what it is you've done. We'll talk later about data management and its benefit in doing this type of development. Actually, processing the assembly code itself, how we create the memory, how we write the assembly code, how we assemble it, all of that's been documented. So please refer to those notes for the mechanics of turning your assembly code into memory inside of the Trailblaze. I wanted to just document in this example. He shows a couple different assemblers that are available for the PicoBlaze and how you would define the instructions. On the left is the definition that would be for our processor. Again, I recommend you to the document that I posted on Beachboard that itemizes all of the instructions that are currently implemented in the Trailblaze, giving the correct reference to each of those instructions. Nice thing is that we'll be able to map our board with our processor. It should be transparent as long as we followed everything correctly. And that's basically it.